Now, we're going to take up one more problem, problem number 63. A compound bar is made up of central steel plate of 50 mm wide and 10 mm thick, to which a copper plate 50 mm wide and 5 mm thick are connected rigidly on each side. The length of the compound bar at room temperature is 1000 mm. If the temperature is raised by 100 degrees centigrade, determine the stresses in each material and change in length of the compound bar. Assume ES equals 200 GPa, EC equals 100 GPa, alpha S is equal to 12 into 10 to the power of minus 6 per degree centigrade, and alpha C, which is equal to 18 into 10 to the power of minus 6 per degree centigrade. Now, so this is the plate wherein you have a 50 by 5 and the steel plate which is covered by two copper plates. Having the area of cross section is 50 into 10 for steel and 50 into 5 for copper. So when the lever after temperature rise, if you are considering the steel plate will go into coefficient thermal expansion will go to be up to here, whereas the copper plate will be up to this. So the steel plate will be under tension and the copper plate will going to be under compression. So what is the area of cross section of steel? The area of cross section of steel is 50 into 10, which is equal to 500 mm square. And then the area of copper is 50 into 5, which will be 2000, which will be 250, 50 into 5, which is 250 into 2. So you're going to get it as 500. So due to temperature rise, steel will expand lesser than the copper. So that is, hence the steel bar will be under tension. That is, you can see here, the steel bar will still have some more length which has to be expanded till it reaches to the lever after temperature rise. And the compression with the copper bar will be under compression because it is exceeding this level. Now, for equilibrium, what is that? Total tension in steel will be equal to the total compression in copper. So what is total tension in steel? That is sigma S into AS will be equal to sigma C into AC. So sigma S into 500 will be equal to sigma C into 500. Therefore, sigma S will be equal to sigma C. Also, we know that final increase in length of steel bar will be equal to final increase in length of copper bar. So what is that final increase in length of the steel bar? That is the free expansion in steel bar plus delta S, that is alpha S into T into LS plus delta S will be equal to alpha C into T into LC minus delta C, because the minus sign here is because it is the copper bar is under compression and steel bar is under tension. Therefore, you are getting plus here and minus here. So what is delta S plus delta C? Delta S plus delta C will be equal to alpha C into T into LC minus alpha S into T into LS. What I am doing is I am rearranging the same equation by taking delta C to the left hand side and alpha S into T into LS to the right hand side. So as we know, what is delta S plus delta C? Delta S is PS into LS by AS into ES plus PC into LC by AC into EC will be equal to, take out the T as the common factor, into alpha C into LC minus alpha S into LS. So what is that? PS by AS, you can write it as sigma S. So sigma S and LS is equal to LC. So sigma S by ES plus sigma C into EC will be equal to alpha C minus alpha S into T. And because LS will be equal to LC, which is equal to 1000 mm. So which has been given in the problem. So what is sigma S? Sigma S by 2 into 10 to the power of 5 plus sigma C into 1 into sigma S, because sigma C is equal to sigma S. So you substitute sigma C as sigma S by 1 into 10 to the power of 5, because this condition sigma S will be equal to sigma C. So then you substitute the value of coefficient of thermal expansion of copper and steel that is 18 into 10 to the power of minus 6 minus 12 into 10 to the power of minus 6. The entire thing is multiplied by the temperature change, that is 100. So on as sigma S is equal to sigma C. So temperature stress induced in the steel bar, so sigma S, on simplification, you will going to get it as 40 Newton per mm square, which is in tensile. Similarly, temperature stress induced in the copper as sigma S is equal to sigma C. So sigma C will be also equal to 40 Newton per mm square in compression. What is the change in length of the compound bar? Change in length of the compound bar will be equal to alpha S into T into Ls plus delta S, that is equal to 12 into 10 to the power of minus 6 into T is temperature rise of 100 into length of steel, which is 1000, plus 40 is delta S is 40 into 1000 divided by 2 into 10 to the power of 5. So that means sigma S into Ls by Es. That is what we want to give. So on simplification, you are going to get it as 1.4 mm. So now, so this is how you will be able to calculate the values. This is how you will be able to solve the problem. Now we're going to take up one more problem. Problem number 64. An aluminium bar tapers from a diameter of 200 mm at one end to 100 mm at the other end over a length of 1000 mm. The bar is stress-free at temperature of 27 degrees centigrade. So that means there is no expansion at the temperature of 27 degrees centigrade. If the temperature drops at 0 degrees centigrade, find the maximum normal stress on the bar if the ends are attached to the rigid supports, which is as shown. EA, aluminium bar of Young's modulus, will be equal to 0.7 into 10 to the power of 5 Newton per mm square. And alpha A, the coefficient of thermal expansion of aluminium, is equal to 24 into 10 to the power of minus 6 per degree centigrade. So how to solve this problem? So what is the temperature drop? Temperature drop is T, that is 27 minus 0, which will be equal to 27 degrees centigrade. So elongation of tapering bar of circular cross section, delta L, will be equal to 4 into P into L by pi into E into D1 into D2. So that is the general expression. So 4 into P into L divided by pi into EA into D1 into D2. So this elongation is numerically equal to the shortening of the bar due to temperature drop. So that means as the temperature is dropping, so that means the temperature is reduced. So naturally there will be a, it will be equal to that elongation is numerically equal to the shortening of the bar. So it will go to reduces in length. So delta L will be equal to alpha A into T into L, that is the coefficient of thermal expansion into temperature drop into length. So alpha A into T into L will be equal to 4 into P into L by pi into EA into D1 into D2. So as length is cancelled both on the left hand side and the right hand side, so that will be equation reduces to what? Alpha A into T will be equal to 4 into P by pi into EA into D1 into D2. But what we know, what we want is the tensile load induced on the bar due to temperature drop, which is P, will be equal to alpha A into T into pi into EA into D1 into D2 by 4, because LL will get cancels. So substitute the values of all the values, that is alpha A, which is 24 into 10 to the power of minus 6 into temperature drop is 27 into pi into Young's modulus of aluminium is 0.7 into 10 to the power of 5 into 100 into 200, because D1 and D2 divided by 4, you will going to get the value as 71,251.3 Newton, which is the maximum stress in the bar. Sigma max will be equal to P by least area of cross section. So what is that? Least area P is 71,251.3 divided by the least area of cross section is pi by 4 into 100 square, which will be equal to 90.72 Newton per mm square. So this is how you will be able to solve this problem. If you find this this video is useful, please subscribe to my channel. Thank you.